Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to continue to be going over intermolecular forces. In this video we'll be going over hydrogen bonding. So to recap what we went over in my last couple of videos, we talked about London dispersion forces and we talked about dipole-dipole interactions. The London dispersion forces are interactions or attractive forces between molecules due to the fluctuation of electron density that creates what is called a temporary dipole between the molecules or the atoms. And so this is typically the interaction that you find in nonpolar molecules because they don't have polarity in the molecules themselves, but they have a polarity that is then induced or that is instantaneous or because of the fluctuation of the electron density at any one moment that then influences neighboring molecules or atoms to also undergo a dipole creation. And so then you get that attractive force between opposite sides of the molecules and the or atoms. And that is very short-lived, so it doesn't last very long, and therefore it's quite weak. And then we talked about dipole-dipole interactions that are permanent dipoles. These are the predominant forces that you find in polar molecules because polar molecules have a permanent dipole. It doesn't go away due to a fluctuation of electron density. It's always there because of the permanent difference in electronegativity between the atoms. The one atom that's more electronegative is going to be permanently pulling on and taking away the electron density, and that electron density is going to be permanently around the more electronegative atom and taking it away from the lesser electronegative atom, creating that permanent dipole. And it's that a permanent dipole that gives the molecule or the atom or the molecule in this case a partial positive side and a partial negative side. And so the partial negative side of one molecule is going to be attracted to the partial positive side of another molecule. So the negative of one side of a molecule is attracted to the positive of another molecule, a neighboring molecule, and so that creates an attractive force, and that attractive force sticks around a lot longer. And so therefore dipole-dipole interactions are stronger than your London dispersion forces. I also want to recap and say that all molecules, all atoms have London dispersion forces regardless of whether you're polar or nonpolar, because all atoms and molecules have electrons and electron density, and there's always going to be fluctuation. So they're all going to have London dispersion forces. The polar molecules are also, in addition to the London dispersion forces, are going to have your dipole-dipole interactions. And the dipole-dipole interactions for polar molecules are typically going to be the predominant attractive force in those molecules. That isn't to say that they don't have London dispersion forces. They just aren't as strong or predominant as the dipole-dipole. But again, that isn't to say that in any molecule, the London dispersion forces are not going to be a large factor. If you remember what we said before, the larger the molecule, the stronger the London dispersion force. So they're still there. But we typically ignore those for polar molecules because, again, they're predominant. The dipole-dipole interactions are predominant. Okay, what about this third category called hydrogen bonding? So this is essentially a strong type of dipole-dipole. It's an especially strong dipole-dipole interaction, and it's the strongest of the intermolecular forces. So IMF for intermolecular forces. And why is that? That's because only molecules that have a hydrogen bonded to one of these three very electronegative atoms. So nitrogen, oxygen, fluorine. So if you have a molecule, and in that molecule you have a hydrogen, and that hydrogen is bonded directly to a nitrogen, oxygen, or fluorine, then that molecule will display hydrogen bonding. So what is exactly hydrogen bonding? Well, here's a picture of two water molecules. So you'll notice that water molecules, they have two hydrogens bonded to oxygen. So that fits our description here. So you have a hydrogen bonded to either nitrogen, oxygen, or fluorine. Here, water has a hydrogen bonded to oxygen. Here you have two hydrogens bonded to oxygen. So water will display hydrogen bonding. So remember what we said about dipole-dipole. So water is a polar molecule, and so it has a permanent dipole. So the negative side is your oxygen. So the oxygen is more electronegative. It's pulling the electron density towards it from the bonds. So from the hydrogen. So you're getting a partial negative charge on the oxygen, and you're getting a partial positive charge on the hydrogens. And so the same thing with this molecule as well. So what that's going to do is it creates a dipole-dipole interaction between neighboring molecules. So the positively charged or the partial positive hydrogen on one water molecule is going to be attracted to the negative lone pairs on your oxygen of another water molecule. And so this right here, ladies and gentlemen, is the hydrogen bond. So let me write that down. So this here, right there, is the hydrogen bond, H bond for short. So that is the hydrogen bond. Remember, these are intermolecular forces between molecules. This here, this bond here, or this bond here, are not the hydrogen bonding. So these are not hydrogen bonds. Those are covalent bonds that are holding the atoms of the water molecule together. The hydrogen bond is between two different water molecules. So this right here is the hydrogen bond. And again, the hydrogen bond is a special dipole-dipole. Why? This is especially strong because we have very electronegative atoms, which are the hydrogen is bonded to. So because of the especially strong electronegativity of oxygen, nitrogen, and fluorine, that's going to pull on the electron density from hydrogen even more. And so such that the polarity is going to be pretty strong, and that's going to create a strong hydrogen bond here. And so again, the negative lone pair on the nitrogen, oxygen, and fluorine of one molecule is attracted to the partially positive hydrogen of another molecule. That's what creates the hydrogen bond. That's your hydrogen bond there. Okay, so that's and so this is the strongest of the three intermolecular forces that we've covered. So the weakest is the London dispersion forces because they are just a temporary dipole that doesn't last very long. Then you have your dipole-dipole, and that is due to the permanent dipole, the polarity of the molecule. And then finally we have hydrogen bonding, which is the strongest of the three. So hydrogen bonding is the strongest of those three, and that's because of the electronegativity of these particular atoms create a stronger polarity in the bonds, and therefore a stronger interaction between the molecules. And so again, that isn't to say that the water molecule or these molecules that have hydrogen bonding don't also have dipole-dipole and London dispersion forces. They do. It's just that the hydrogen bonding is the predominant force that we look at, and that seems to be the one. But they still have dipole-dipole interactions because they're polar molecules. They still have London dispersion forces because they have electrons as well. So keep that in mind. So the last thing I want to cover is a little flow chart to help you remember. So the question you want to ask yourself is the molecule polar? That'll get you started. So if it's not polar, then the only intermolecular force that molecule will have is going to be LDF, London dispersion forces. So again, if your answer to the question is is the molecule polar? If that's a no, then London dispersion forces are the only forces that that molecule or atom can have or will have. If the answer to the question is the molecule polar is yes, then the next question is, does the molecule have an NH bond or an OH bond or an FH bond in the molecule? If it is a yes, then it will display hydrogen bonding, which is the strongest of the three, but it will also have dipole-dipole interactions and it will have London dispersion forces. If the answer to the question is no, it does not have NH, OH, or FH bonds in the molecule, then it will display dipole-dipole interactions and it will have London dispersion forces, but no hydrogen bonding. So this is a nice flowchart to help you figure out what kind of intermolecular forces a particular molecule or atom will have. I hope this video was helpful. I hope you enjoyed it. If you did, please hit that like button, share the video with your friends, families, relatives, anyone. If you like my videos, please subscribe to my channel. Hit that notification right up there, and so that way you can be notified by other videos I put out. Please put a comment down below in the comment section. Let me know what you think. Ask me questions. I'd love to hear from you. Thanks for joining me, and have a great day.